Every second, the sun converts 600 million tons of hydrogen into helium and releases more energy than humanity has used in its entire existence. For 70 years, scientists have been trying to recreate that process here on Earth. The idea is simple. Take hydrogen, the most abundant element in the universe, heat it to 150 million degrees, and fuse the atoms together. What you get is energy. Enormous, practically unlimited, carbon-free energy. No meltdown risk. No long-lived radioactive waste. No dependence on weather or geography. Just the power of a star contained in a machine. It sounds too good to be true. And for 7 decades it has been. Fusion has become the most expensive joke in science. Always 30 years away and always will be. But something has changed. In the last 3 years, billions of dollars have flooded in. Breakthroughs that were thought impossible have happened. And for the first time in history, serious people are betting real money that fusion power will reach the grid within their lifetimes. So is this finally it? Or is fusion still a mirage? Here's how fusion works. You take 2 isotopes of hydrogen, deuterium, which you can extract from seawater, and tritium, which is made from lithium. You heat them to around 150 million degrees Celsius. That's 10 times hotter than the core of the sun. At that temperature, the atoms stop being atoms. They become plasma, a superheated gas where electrons are stripped from their nuclei. If you can squeeze this plasma hard enough and keep it stable long enough, the hydrogen nuclei overcome their natural repulsion and fuse together into helium. That fusion releases a neutron and a massive burst of energy. 1 gram of fusion fuel contains the energy equivalent of 8 tons of oil. The challenge is containment. How do you hold something that's 10 times hotter than the sun? You can't use any physical material. It would vaporize instantly. The answer is magnets. Incredibly powerful superconducting magnets that create a magnetic cage, forcing the plasma to spin in a donut-shaped loop without ever touching the walls. This device is called a tokamak, and for 70 years it has been the most promising path to fusion energy. The quest for fusion began in the 1950s, when both the United States and the Soviet Union realized that the same physics behind the hydrogen bomb could theoretically be harnessed for peaceful energy production. Early optimism was enormous. Scientists genuinely believed they'd crack fusion within a few decades. They were wrong. Every time engineers solved one problem, 3 more appeared. The plasma was unstable. The magnets weren't strong enough. The energy going in was always more than the energy coming out. By the 1970s and 80s, governments poured billions into massive projects. The Joint European Torus in the UK, the Tokamak fusion test reactor at Princeton. Each one got closer, but none crossed the finish line. Then came ITER, the International Thermonuclear Experimental Reactor. Announced in 1985, designed by 7 nations, intended to be the machine that would finally prove fusion works at industrial scale. Its original budget was around $5 billion. Its original completion date was 2016. Today, ITER sits half-built in southern France. The budget has ballooned to over $20 billion. The timeline has been pushed to 2039. Manufacturing defects, regulatory delays, management chaos. ITER has become, to its critics, the ultimate symbol of fusion's broken promises. And then, on December 5th, 2022, something happened that changed everything. At the National Ignition Facility in Livermore, California, 192 of the world's most powerful lasers fired simultaneously at a target the size of a peppercorn, a tiny capsule of frozen hydrogen. The lasers delivered 2.05 megajoules of energy. The fusion reaction that followed produced 3.15 megajoules. For the first time in human history, a fusion reaction had produced more energy than was put into it. Ignition had been achieved. The physics worked. Fusion wasn't just a theory anymore. It had been proven in a laboratory. Now, to be clear, The entire NIF facility used 300 megajoules of electricity to power those lasers. So the net energy balance was still deeply negative. But the principle had been demonstrated, and that demonstration sent a shockwave through the energy world. Because if the physics worked, maybe the engineering was just a matter of time and money. And the money started flooding in. By the start of 2026, private investment in fusion had surpassed $12 billion. Not from governments, from venture capitalists, tech billionaires, and energy companies who smell the biggest opportunity in history. Commonwealth Fusion Systems, backed by Bill Gates and Google, has raised nearly $3 billion. They're building a compact tokamak called Spark in Massachusetts, using revolutionary high-temperature superconducting magnets that are far more powerful than anything ITER uses, in a machine a fraction of the size. Spark is expected to switch on in late 2026 and produce net energy gain by 2027. Then there's Helion Energy, funded by Sam Altman of OpenAI. Helion has taken a completely different approach. Not tokamak. They fire two plasma rings at each other at 1,000,000 miles per hour and capture the energy directly from the magnetic field. Microsoft has already signed a contract to buy fusion electricity from Helion by 2028. In China, the East reactor set records by exceeding what physicists call the Greenwald limit by 70%, proving fusion reactors can be far more powerful than previously thought. In France, the West reactor held a stable plasma for over 20 minutes. This isn't science fiction anymore. These are real machines in real buildings hitting real milestones. The US Department of Energy published a roadmap in 2025 targeting fusion on the grid by the mid-2030s. But here's what the press releases don't tell you. Fusion still has enormous unsolved problems, and some of them might be deal breakers. Problem 1. Tritium. The fuel you need for fusion doesn't exist in nature in useful quantities. Tritium has a half-life of just 12.3 years, which means it decays rapidly. The plan is for fusion reactors to breed their own tritium by surrounding the reactor with a blanket of lithium that absorbs neutrons and produces new tritium. But nobody has ever built a working tritium breeding blanket at scale. A single reactor needs 168 kilograms of tritium per year. The entire world's current supply is around 25 kilograms. Problem 2. Neutron damage. Every fusion reaction fires high-energy neutrons into the reactor walls. Over time, this radiation degrades the metal, making it brittle and radioactive. No material has been proven to withstand years of continuous fusion bombardment. We literally don't know if the reactor walls will survive. Problem 3. Engineering complexity. Maintaining a plasma at 150 million degrees, surrounded by superconducting magnets cooled to near absolute zero, while breeding tritium, extracting heat, and generating electricity all at once continuously for decades. No one has done it. No one is close to doing it. The physics may be solved. The engineering is not. So will nuclear fusion actually power the world? The honest answer is that nobody knows. The optimists point to the explosion of private investment, the breakthroughs at NIF, the pace of magnet technology, and the ambition of companies like Helion and Commonwealth Fusion. They say fusion is no longer 30 years away. It's 10 to 15, maybe less. The skeptics point to ITER's endless delays, the unsolved tritium problem, the material science gap, and the fact that every fusion timeline in history has slipped. They say we should invest in proven renewables, solar and wind and batteries, rather than chasing a technology that has consumed billions and delivered nothing to the grid. The truth is probably somewhere in between. Fusion will almost certainly work in a laboratory. The physics is proven. But turning a laboratory result into a power plant that operates reliably, economically, and for decades, that's a different challenge entirely. And it may take longer than anyone wants to admit. What's different this time is that for the first time, the smartest money in the world is betting that the engineering can be solved. And when that much money, talent, and ambition is aimed at a single problem, history suggests something usually happens. The question isn't whether fusion will work. The question is whether it will arrive in time to matter. Thanks for watching. If you found this useful, subscribe for more videos on the forces shaping our future.